the next thing we take up is the idea of specific algebraic structures, and we can begin by saying a group. So, group as an algebraic structure. Since we already discussed those generic properties, we can write down quickly now, but the axioms are usually stated as follows. Closure, that is, the set S is such that given any two elements in it, and if you combine them using this binary operation, whatever you have, you get back something within the set. Okay. So, if A and B belong to S, then A O B necessary belongs to S. So, we have a set S with a binary operation O, we can say then the first requirement is closure. Sometimes it looks a little trivial, but it turns out that it is important. Sometimes you can fall out of the original set that you have in mind. So then the closure itself would be violated. Number 2 is associativity. So that we already talked about. Then there should be an identity. For it to be a group, there has to be an identity operation, meaning some operation which actually doesn't change anything. Okay. So the statement is that there exists E such that AOE is equal to A and is same as EOA. But as I said, purists say that it's not necessary to add both sides, you can get one from the other. And fourth is inverse. There always exists an A inverse for every A. And of course, A inverse belonging to S for every A belonging to S, such that A inverse OA is identity. And it turns out that left identity and right identity are usually the same. So these 4 axioms define what is a group. Okay. And two very common examples we can immediately pick up are matrix multiplication of square matrices. Square matrices of a fixed size, say 3 by 3, 5 by 5, any n by n fixed size square matrices. We can see that under matrix multiplication, you will get another matrix of the same size, so there is closure. A matrix multiplication is associative, as you know, so you get associativity. The identity element is the diagonal 1, 1, 1 matrix, which, as you know, leaves a matrix, any other matrix unchanged if you multiply it on left or on right. And the inverse exists only for determinant not equal to 0. So if you don't have, so example is of determinant not equal to 0. Then you can always invert such a matrix. So the inverse then exists. So this is a very standard example. A geometric example is, so we can say examples and put this as number 1, and number 2 is rotations of a rigid body, of a rigid object. So you can think of any, you take a pen and then say you rotate it, you combine it with any one rotation is one operation. So the set S in that case will be all possible configurations of the pen, all the possible ways it could be lying, and you start with any one way it is lying, you can always bring it to any other, and that is one operation. But if you combine two such operations, you rotate it from one configuration, so let us say with a 1 point fixed, so to make things a bit simpler, and then you can always rotate it to one configuration, you can then rotate it to another configuration. That combination of two rotations is yet another which could have been done directly as well. Okay, it could be rotation about some third axis. Associativity is there for rotations because you can do them in this sequence, it doesn't matter, that has to be checked of course. The identity is you do nothing, so that operation you don't rotate it at all, so the identity operation exists, and the inverse is you undo the rotation. So Euler proved an important theorem in early days of dynamics that said any general motion of a rigid object is translation plus some 3D rotation about a fixed point in the object. So that's an important way of characterizing, actually now you can use it in reverse to characterize a rigid body, but rotations were studied in great detail by Euler, so in that sense he had done group theory in its preliminary form right then, although he didn't emphasize the group structure at that time, but he specified all the machinery required to grapple with rotations. They are called Euler angles, which in mechanics you will probably learn. All right, so that lays out the very basic requirements of a group. These are the most essential requirements of a group. In addition, there is a fifth property, which is commutativity, which simplifies it. It's an additional requirement, so it's more restriction. Which is optional, and that is commutativity. And if this additional axiom is satisfied, then it is called an abelian group. Then it is called abelian or commutative group. So rotations about a fixed axis. Rotations of a rigid body. Or you can just think in terms of rotations in the plane, rotation of vectors, let us say, in 2D plane. This is the simplest example of an abelian group, and we deal with it all the time. So you may be, let me just write out how it works. So I have x and y axes, and let us say I have position vector in 2 dimensions. So it has components x and y, and then I can rotate the vector to a new position where it may have components x prime and y prime. And the angle through which it rotates is theta. Then we know that x prime, y prime written as a column vector can be written out as a cos theta sin theta matrix. So if you think of the same vector as having rotated, its x component is reducing. So it is cos theta and minus sin theta y. So x prime will be equal to cos theta x minus sin theta y, and there will be sin theta x plus cos theta. So y prime will be equal to this. So y prime has cos theta times y. As you know, when theta goes to 0, you should recover x prime y prime should be same as xy. So when theta is equal to 0, it becomes diagonal identity element. And then for all other angles theta, so the group here, you can think of it in different ways. We already have abstracted in the sense of we are talking about vectors, we are not talking of much of a physical quantity. The first one is actually you can think of a pen and think of rotations in a plane of about a fixed axis of the pen. But when we talked of vector, we already became a little abstract. But furthermore, you can now think simply in terms of these 2 by 2 matrices, and then say my set consists of 2 by 2 matrices. This obviously has determinant 1 because cos squared plus sin squared will be equal to 1. So 2 by 2 matrices of determinant 1, we can easily check that they form a group because the product of any 2 of them will just be another rotation, and inverse will be just rotating backward. Identity is when it is identity. Associativity is inherited simply because it's a matrix. But furthermore, it will be commutative because you rotate by theta 1 and then by theta 2, it is same as rotating by theta 2 first and then theta 1. So the set of matrices, 2 by 2 matrices of size determinant 1 and determinant 1 is an abelian group. So that group would be called SO2. So this is like giving a trailer to what will come later. So the set of matrices treated as group is denoted SO2. O means orthogonal because these matrices also have the property that the transpose is the inverse. So they are orthogonal matrices, the size is 2, and S is for special orthogonal group means that they have determinant 1. Okay, so this is these are the essentials of a group. The next thing I want to cover is vector space, which you are all familiar with. You have been using Newtonian vectors for quite a while. The word linear is often not even mentioned. Vector space is generically linear. So what is a vector space? Basically you have a set of vectors set V with two kinds of operations, plus and dot. So the plus is the linearity part, that you can add anything, and the dot is multiplication by scalars. So there is V with plus and dot and an auxiliary set of scalars. And of course the dot enters only if you have those scalars. So the axioms can be stated in two parts. Under plus, the set forms an abelian group, okay, because there is closure, there is associativity of addition, identity element is because there is a zero vector and inverse is negative of a vector. So under plus, an abelian group, and it is abelian, right? A plus b vector is same as b in any n dimensions, it's nothing to do with 2 dimensions. So under plus, an abelian group, and under scalar multiplication, it is linear and it is distributive. So we can say A dot V1, A dot V is also belongs to V. So let us say the set of scalars is S, and A is distributive, so that is the word used, distributive. In other words, A V1 plus V2 is same as A V1 plus A V2. Additionally, the scalars also have algebraic structure of their own, so that their own abelian structure, with a sign which without much fuss is called the same sign plus, although that plus is technically different from the plus of the vector space, so that A1 plus A2 also belongs to S, etc. And then we have the third property. So here I will put these 1, 2 and 3. Third being that A1 plus A2 V is same as A1 V plus A2 V. So there are two pluses, but you can see that they merge, because here it is sum of only the scalars, but here is sum of the two vectors. So as you, it's very easily a transferred property, and people don't distinguish between the two plus signs. This vector space structure is very important and worth keeping in mind, because we will be using it a lot. And it will be used especially when we get to representation theory. Groups are represented usually as acting on vectors, like we already did, right? This example we saw was algebraically you can think of this as this set of matrices, but geometrically you can think of this as operations on two-dimensional vectors. So we already have sort of a trailer of what is going to come later. There is an abstract group where you may just specify a list, you can just specify a table. You have some elements G1, G2, Gn. You just specify a 2 by 2 table which specifies what is G1 times G2, G1 times G5, etc. That is sufficient to make it a group, provided the axioms are satisfied, associativity and so on. But then in practice, that is not how you actually use the group. You use it by using those G elements as operations on something else. So the other classic example is permutations. So we can actually move to that. But just to finish what I was saying here, we will always have these two versions of thinking. Either you think only of the set of matrices and their properties and think of it as a group, or you think of it in terms of how it affects two-dimensional vectors. The advantage of this second way of thinking is that you could have also created matrices. You can have higher dimensional representations, which we will see later. Okay, so the representations can be many for the same group. The same group may be realized in more ways than one. So you can think of, say, moment of inertia tensor, and so we will come to the examples later, more detailed examples later. But there are groups by themselves and their general properties, and then how they affect a particular representation, where they are realized as actions on something. So one such classic example is permutations as actions. Okay, so the permutation group is the group of all possible ways of group consisting of the action, okay, all possible ways of rearranging say n objects the possible ways are group elements. So we can see that this particular example, permuting objects, is actually a group, because you think of one particular permutation as one group element, then you think of another permutation as another group element. Now you know that if you do them in sequence, you first do one permutation and then follow it by another permutation, it is again after all permutation of the same set, so you will get some other permutation. So there is closure. This is the first thing. So we can verify this. So given any example, you have to mentally or physically or through some modeling go through the exercise of checking these things. So is there closure for permutations? Well, yes. Then the question is whether they are associative. This requires work, but one can do it, needs to be checked. And identity of course exists, because you don't permute, you don't do anything to that set of objects, then you have identity. And then inverse means you undo the permutation, you go back to the previous one. Now permutations are very interesting, because it turns out that, and this theorem we will prove next time, that any discrete group is a subgroup of some permutation group. Okay. So there always exists some permutation group of whose the discrete group of your interest is going to be always subset of some permutation group. So we will prove that next time, but this is a very important and interesting reason why permutation groups are studied, and we develop special notation for discussing the permutation groups. So before we go on, let us do the last bit of algebraic preliminaries. The reason why we mention permutations is that thought of as operations, they are obviously a group, but additionally you can realize them as matrices by drawing. If you have n objects, then you write the n objects as a vector, and then any operation is basically exchanging them. So you can write out the so representations can be represented as matrices. So this was also meant to give you an example of what is a group and what is a representation. So the group you can specify simply by listing what permutation followed by which permutation will give you which new permutation in a list of permutations only. But then you can write out matrices which will actually, under matrix multiplication, reproduce what would have happened to the permutations. So that is the idea of representation. So the final interesting algebraic structure that we want to discuss, or algebraic concept, is the concept of equivalence relation. This is a very cute idea, looks very simple but is very far reaching. So we say that for a set S, a relation R is a conditional about A, B, etc. belonging to S, such that A is always related to A. So you give some condition. Okay. For example, you say straight lines in the plane. A straight line is related to another straight line provided it is parallel. A straight line A and straight line L1 and straight line L2 are related if they are parallel and not related if they are not parallel. So you can set up some kind of a condition property of straight lines in the plane, and another one can think of is perpendicular property. So these two are interesting simple examples. You say that one straight line is related to another if it is perpendicular, and we will see how the axioms we are saying are going to work in the two cases. So we say that a set is an equivalence relation if three conditions are satisfied by that relation R. An object should be related to itself. Now, if you think of family relation, although mathematics is not going to work there very well, certainly you are related to yourself, so it would work there. Number 2, A R B means that B are A. Okay, and if you generically say blood relative or something like that, then yes, if A is related to B, then B is related to A. But if you say something like brother of, then it may not work in reverse because the other person may be sister. So this is where these properties are important. You have to specify what the relation R is. And the third thing is transitivity. If A are B and B are C, then A is related to C. A are B and B are C, then that implies that A must be related to C. So these are called reflexivity. This is called symmetry. Sorry about that. And this is called transitivity. It carries on. If A is related to B and B is related to C, then A is also related to C. So a relation R satisfying these is called equivalence relation. You can think of many relations and they will not satisfy these. So it is a very powerful requirement actually. These properties is called equivalence relation. And we will see a very important consequence that this has very shortly. But we can now look at our two examples we thought of, parallel and perpendicular. So if you say that parallel is my relation, then any line is parallel to itself. So it satisfies reflexivity. If L1 is parallel to L2, then naturally L2 is parallel to L1, so it satisfies symmetry. And if L1 is parallel to L2 and L2 is parallel to some line L3, then it will also follow that L1 will be parallel to L3. So in the plane, the is parallel is a property that is an equivalence relation. But let us look at the perpendicular. It fails the very first requirement because a line is not perpendicular to itself. Okay. So is perpendicular to is not an equivalence relation. Now let us state the important theorem. The theorem is that if you have an equivalence relation in a set, then that relation divides the set into mutually non-intersecting subsets. Okay. Divides a set into disjoint subsets. So pictorially I think of it like this. This is my big set and I will end up forming subsets such that no two of them will overlap. Now it is easy to see why, I mean we can prove why this happens. That so think of let S1 how should we call it, yeah, S1, S2 etc. be some subsets, let S1 be such that all elements in it are related to each other. Related by R. Now, first we prove that there is nothing in S which is not already inside S1. This is so S1 is a very uniquely defined set in S, because any other element that belongs to S has to be included in it because all the elements that are related are included in S1. And if you have any other set S2, then no element of S1 can be related to any element in S2, because if any one gets related to S2, then through transitivity all the elements of S2 get related to all the elements in S1, then essentially S1 and S2 are the same subset. Okay. So similarly, let us say S2. Now, S1 necessarily is disjoint from S2, because if A1 belongs to S1 and B, so A belongs to S1 and B belongs to S2, and hypothesis A says related to B, then this hypothesis forces you to conclude that S1 and S2 have to be same sets, because have to be same subsets. Due to transitivity. Right, because so once you declare that A here is related to B there, then because of transitivity, since this A is related to everyone here, but it is now related to B, therefore B by transitivity is also related to all. In other words, you get a new set. This whole thing has to be really one set by itself. Okay. So either the two sets are disjoint or they are the same. And furthermore, because the equivalence relation actually exists over the whole set, it covers all the possible elements in the set. So the union of all the disjoint subsets does make up the set back as well. So that's also important to know. So you may have n number of elements in it which are not related to anyone except themselves. The reflexivity holds, but it doesn't relate to any other. So I have a special element A which relates to of itself, the property specified such that it relates, but it need not be related to anything else. This point will by itself be a set, a subset, a single point subset, and you can have several of them. But any other set which any other subset which contains several elements will be other category of subsets. But these two categories will exhaust all the possible subsets you can have, and the union of all such subsets which are all disjoint, that union will make up the original set back again. So it is a very nice partition of the whole set, that is implied by present existence of an equivalence relation. So, but as I said, not all relations are equivalence relations, and not all sets may admit such nice equivalence relations. But it is going to be a very important concept that we will use in proving some of the things. Okay, so I think we can end with this here today.